Theorems 6 and 7 are associated with the question of asking the probability that two or more events will all happen or both happen out of two or more events. So this is in the form of asking the probability of event A and event B. So before we introduce these two theorems, we need to get clear about a concept of independence. So events are independent if one's occurrence has no influence on the probability of the other event or events. So that means if event A occurs, then it doesn't increase or decrease the probability of event B's occurrence. So they just have no effect, no influence on each other. And independence event occurs in three situations: when you repeat an action that doesn't move any possible outcomes, or you repeat an action that does remove a possible outcome, but then the outcome is replaced before the next action takes place. The three is that you use two different random elements. So the key is that if the events are independent, then the occurrence of one event does not change the sample space. Theorem 6 says that if A and B are independent events, then the probability of both A and B occurring is the product of their respective probabilities. So this is the probability that event A occurred, and then given that event A occurred, event B still have the probability of PB to occur, and therefore I times the PB. So this is the probability of both A and B occur. Here's an example for the first situation of getting independent events. So if you repeat an action that doesn't remove any possible outcomes, then your previous action and your following action, they are independent events. So the events associated with like a first action and a second action has no effect on each other. So for example, you roll a dice twice. What is the probability that a 6 is not obtained in the first roll but obtained in the second roll? So the sample space is 1, 2, 3, 4, 5, and 6. When you roll a dice, it doesn't change the sample space. So after the first roll, and then you start to roll the second roll, and it has the same. It just has the same probability of getting 1, 2, 3, 4, 5, or 6. It has nothing to do with your first roll. So they are totally independent events. For example, the event A is that the first roll does not get a 6. So the event A contains these 5 outcomes. So the PA equals to 5 over 6. And then the event B is that the second roll gets a 6. So then B contains only one event 6. And therefore the PB is 1 over 6. And therefore, the occurrence of A and B does not affect each other, so the probability of both A and B occurs. So that means in your first roll, you didn't get a 6, but then in your second roll, you get a 6. So that is 5 over 6 times the 1 over 6. And I want to note that it's just the coincidence that this A and B they do not have overlap in the outcomes, but for the independent examples, they could have overlaps in the outcomes because they are just totally independent. For example, my event B could be that the second roll does not get a 6, neither. And then the B will be the same as the A, 1, 2, 3, 4, 5. And then if I ask you to find the probability that neither the first roll nor the second roll get a 6, then the probability will be 5 over 6 times 5 over 6. This is because your first roll and your second roll are independent. The second situation of getting independent events is called drawing with replacement. So you repeat an action that does remove a possible outcome, but then you replace this outcome before the next action takes place. So before the next action takes place, the sample space has been restored to the original form, so therefore the sample space does not change. And let's have a look at the example 7.7 in our textbook. So if these 261 parts described in this table, as we have used for our previous examples, if these 261 parts are contained in a box, what is the probability that 2 randomly selected parts will be from supplier X and supplier Y? So assume that the first part is returned to the box before the second part is selected. And therefore our sample space is 261 parts. So before the first row, we select a part from X, right? This is the event A in the first row. And then in the second row, before the second row, we put the first part back to the box. So therefore, before the second row, our sample space is still these 261 parts. And therefore, the event A and event B are independent. So the probability of both A and B occurs, of both X and Y, the parts from X and parts from Y are drawn. It's just the Px times the Py. Here is a graphic illustration of this example. So event A is to select a part from X in the first row, and before the first row, we have these 261 parts. So after the first part is selected, and then we return it to the box before the second part is selected, and therefore the sample space does not change. So as you can see, we still have 261 parts here, and then the event B is to select a part from Y out of these 261 parts. So the occurrence of A does not affect the occurrence of B, and on the other hand, the occurrence of B does not affect the occurrence of A. To put in another words, selecting a part from X in the first row does not increase or decrease the probability of selecting a part from Y in the second row, and vice versa, because we return the parts and we restore the sample space to the 261 parts. Here is the third situation to get independent events, is that if you use 2 different random elements. So in this situation, you actually have 2 different sample space for your 2 experiments. And therefore, the event from each experiment are independent. So this is very intuitive. For example, you draw a card from a deck of 52 cards, and then you roll a dice. What is the probability of drawing a 5 and then rolling a 5? So your sample space are totally different. The sample space for event A is the 52 cards, right? And then the sample space for event B is rolling the dice, so the 6 sides of the dice. And event A comprise of the 4 fives out of these 52 cards. So PA equals to 4 over 55. And this event B is this 5, the side with 5 spots, right? So it only comprises 1 outcome, and therefore the PB is 1 out of 6. Therefore, the probability of both A and B occurring is the PA times PB, so 4 over 52 times 1 over 6.